Okay, our kind of goal for today is to be able to work with a bunch of KC expressions and calculate some KC constants, so some equilibrium constants. I just want you to turn your attention to the board really quickly, because I forgot to write something in here. So today and tomorrow we're going to be finishing up 15.1. This will be the end of our 15.1 notes. And then the following day, on Wednesday, we're going to have a quiz. And the quiz is going to be on basically all of 15.1. Now, I will put up a checklist tomorrow of the things that are specifically on the quiz. But you hopefully know, I mean, there's going to be a question on dynamic equilibrium, right? That was a big rock of our curriculum so far. There's going to be an ice table question because, like I said, that's a pretty big rock so far. There's going to be, you're going to have to do something with KCs, right? That's a pretty big rock so far. So anyways, we'll talk about a bunch of stuff today, and then tomorrow I will put up like a more specific checklist of everything that you will be asked to know for the quiz. Please remember back. I know sometimes our brains can melt over the weekend, and that's totally fine. That's a very natural human thing to do. But please try to remember back when we were talking about KC values. And if I have a KC of, I don't know, 0.31, what I want to know is that trying to indicate to you that this reaction, whatever the reaction is the reaction that's associated with this constant products favored or reactants favored? How do you know, Kate? It's less than 1. Well, what does that mean? Why do you know something that's less than 1 means reactants favored? How could you kind of reason this out for me? It's pretty tough. In general, what is every equilibrium constant equal to in general? Products over reactants, right? So if this is equal to products in general over reactants, right? Okay, well, if this number is less than 1, then what does that mean is bigger? Is the top bigger or is the bottom bigger? The bottom has to be bigger, would you agree? If a number is less than 1, then that means this fraction, whatever this is associated with, like, how could I write 0.31 as a fraction? 31 over 100, right? Just kind of working everything out logically. So this is kind of equal to 31 over 100. Hopefully that makes sense. Yeah. This is reactants favored, right? Totally, 100% it's reactants favored. So you don't, I just want to be very clear, you don't have to memorize this information. You don't have to memorize that a KC greater than 1 is products favored and a KC less than 1 is reactants favored. You can work it out if you wanted to. But you can only work it out if you really truly understand what an equilibrium constant is, right? An equilibrium constant is always, in general, products over reactants. And we're going to come back to that a little bit later. Let's start something new. Let's start talking about what this number is affected by. So I'm going to, below here, I'm going to draw a very in general reaction, okay? 3 A's plus a B gives us 2 C's and a D. Whatever. Here's our reaction, sure, whatever. Now, let's say this KC had a value of 0.31. Now remember, okay, that means Reactants favored. Which of these substances, which of these four substances do you expect to have the highest concentration once equilibrium has been established? Which of these concentrations do you expect, oh, they should probably have the highest concentration once equilibrium has been established? What I want you to think about is, what does reactants favored mean? What are the reactants in this equation? Are they C and D, or are they A and B? Yeah. They're A and B, right? Reactants are always on the left-hand side. These are always reactants, and these are always products. So if we're saying reactants favored, that means, in general, this reaction tends to have higher concentrations of reactants. That's what that means. In general, these concentrations will be higher than those concentrations. And it just, all it does is it just depends on this particular reaction. Now, we can change this value. I'm going to say the Kc for this reaction is 0.31 at what temperature? What do you want it to be at? And just name any temperature.
97 degrees.
Sure, at 97, 200 and 300. Holy crap. Good, at 370 Kelvin. Woo! Holy guacamole, that was really tough. So this Kc only applies at a specific temperature. As soon as you change the temperature, what you end up doing is you end up giving more energy for both of these sides, right? For everything in this, remember, all of these substances are all mixed together in a jar or a reaction vessel or something like that. What happens when you add energy or when you increase the temperature in a system? What happens to all of these chemicals? If I had a jar and it was full of a bunch of particles, right? A's, B's, C's, and D's. If I give this system more energy, if I heat it up, what happens to these particles? Their speed is going to what? Increase, right? They're going to increase, okay? And so if all of these particles start moving faster, do they collide more often or less often? If these particles, let's say it's really cold, okay? Let's say this is only at 25 degrees Celsius, right? So these particles are moving a little bit fast, right? They're bouncing off the walls of the container and they're bouncing off each other, okay? What's going to happen when we increase the velocity of these particles? Are they going to collide more often or less often? They're going to collide more often, right? If they speed up, they're going to collide more often. So what that means is when we increase the temperature, we're increasing the rate of the forwards reaction and we're increasing the rate of the reverse reaction. But we increase them at different amounts, okay? And there's no way for you to tell right now until we get to 15.2. That's what 15.2 is kind of about, okay? So how can we change Kc? What's the only thing we can do to change this Kc? Remember, this Kc is only true at this temperature. So what happens if we change the temperature? What do we also change?
The velocity.
We change the velocity of these particles, and that changes the value of Kc, right? Kc is only affected by temperature. Kc is not affected by changes in concentration. That doesn't do anything to Kc for the most part. Kc is not affected by changes in volume. It's not affected by changes in pressure. And the very last thing, Kc is not affected by the addition of catalysts. Is that how you spell catalysts? Sure, why not? The only way you can change the Kc value for a particular chemical reaction is by changing the temperature of that reaction. So most of the time I will tell you, okay, I'm not trying to distract you when I say, oh, the Kc for this reaction is 0.31 at 370 Kelvin. I'm not trying to tell you that you have to use that temperature. I'm trying to tell you that this Kc value only applies at that temperature. What if we were at 500 Kelvin? Could we use this Kc value to do anything? No, you couldn't do it. You couldn't use it for anything, right? So it's totally useless information if you're not at that temperature. We're gonna go back to our information on, I don't know, do you remember the reaction, right? Do you remember the reaction of hydrogen gas plus iodine gas gives us 2 hydrogen iodides? Do you recall talking about this system? Yeah. So predict whether the equilibrium constant in the 3 systems above will be greater or less than 1. So let's see. System number 1, what do you think? Do you think system number 1, is it going to have a Kc of greater than 1 or less than 1? Hands up for greater than 1. Hands up for less than 1. Okay. We'll see. You write it down. Okay? System number 2 is probably going to be the same thing whichever way you predicted it, and system number 3 is going to be the same thing whichever way you predicted it. Let's take a look at this. Which of these are reactants and which of these are products? So these are reactants and these are products, right? And so what does it look like? Does it look like this system is reactants favored or products favored? In every single case, it appears like it's products favored, right? So we assume, we're going to guess that all of these Kc's should be greater than 1. That's our prediction. But let's see if that's the case. Let's calculate the Kc for all 3 systems. Now, what I want to be very clear on is the equilibrium constant. You only care about the concentrations at equilibrium. We don't care about the initial concentrations at all. We only care about equilibrium. So just keep that in the back of your mind when we're calculating Kc. What will the Kc, in general, what will the Kc for this reaction be? It's products over reactants, yeah, but what is it specifically? What's our only product here? HI. Okay, so it's the concentration of HI raised to the power what? Raised to the power 2, because that's the coefficient. Divided by what? The concentration of H2 multiplied by the concentration of I2. So for trial number 1, let's calculate these concentrations for trial number 1 or system number 1. what is the concentration of HI? What is the concentration of HI in trial number 1? 7.8 what? Millimoles per liter. Okay? I want to be very, 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 very clear. When you do this, what units do you have to use all the time? Moles per liter. Okay? So instead of writing millimoles per liter, what could we write instead of milli? Does anybody know? I'm going to write 7.8 times 10 to the negative 3 moles per liter. Oh, that's terrible. Squared. The reason why I know milli is times 10 to the negative 3 is because it's in your data booklet. I just want to really quickly show you it is in your data booklet. Pretty close to the front after the periodic table. On page 3 of your data booklet. So if you don't want something to be milli something, you can just literally trade the letter M for times 10 to the power of negative 3, right? That's something that you can do. Okay. So just that's a little bit of a recap. So 7.8 times 10 to the negative 3 millimoles per liter, or sorry, moles per liter. The concentration of H2 is 1.1 times 10 to the negative 3 moles per liter. And the concentration of I2 is the exact same thing. So is it okay with you, instead of writing 1.1 times 10 to the negative 3 again, what else could I write? Just squared. Is that okay? Do we understand why I did that?
Yeah.
It's because the concentration of H2 and I2 are the same thing, but instead of writing the same thing twice in a row, I can just write this squared. So I want you to try this out. Try this out in your calculator. 7.8 times 10 to the negative 3 squared divided by 1.1 times 10 to the negative 2 squared. Oh. I get to show you my illegally downloaded calculator. Yeah, that's what I'm talking about. Okay, so the way I would do this is I would go bracket 7.8. Hey, instead of writing times 10 raised to the power of, what should I write? E, the EE button or the E button, right? Second, comma, so that's E. That E means times 10 to the power of, and what's our exponent here? Negative 3, so I'll write negative 3, and then bracket, and then I'll square it, divided by bracket 1.1 times 10 to the power of negative 3, bracket, and then I'll square it. Let's see if you got the exact same thing I got. I got 5.0 times 10 to the negative 11. That's not what you should get, should you?
No.
No. Why is that? 7.8 times 10 to the negative 3 squared divided by 1.1 times 10 to the negative 3 squared. Is the number correct?
Yes,
Yeah,
and
it
1.10.
We'll come back to that. That's very odd. If anybody, yeah.
Is the calculator more in scientific mode? Because I switched my calculator, I think, to scientific mode, and I got that answer.
No, it comes up just in a default setting. Whatever, we'll come back to that. What should it be? It should be 50, right? 50.2. Man, that's weird. 50.2, or if we round it to the correct number of significant digits, yes, it should be 50.3. Sorry, 50.3. Okay, perfect. What I would like you to do is, as quickly as you can, I'm not going to, but as quickly as you can, calculate the Kc for system number 2 and system number 3, and just make sure that it's still kind of the same as 50, right? Do that for system number 2 and 3. And I'm going to figure out what's wrong with my calculator. Oh, yeah. Oh, does anybody need a calculator? Does anybody want a calculator? Yeah? Classic. I love it. John, do you want a calculator? Don't be embarrassed, right?
I just too lazy to go over.
Yeah, that's the worst calculator in the bunch. Use a different one. I should actually throw that in the trash or recycle it.
Yes, it can be. Yeah.
I'm seeing lots of 49s for the second one. Yes, system number 2, and then system number 3 is at 51. Is that what we're getting? Okay, good. So as long as you're good, then I'm good, then we're good, and it's all good. No problem. So let me know if you have any questions. Let me know if you don't know how to use, like if you're having trouble with your calculator, as much as I'm having trouble with my calculator, it makes me look like I'm not an expert, but I really kind of am. Okay, you're just gonna have to trust me on that. I would love to help you out with your calculator problems if you're having any. Let's scooch on and let's try to see if we can use an ice table to be able to help us out with any KC problem. Okay, we can use ice tables to help us determine the value of an equilibrium constant for a reaction. Now, in general, again, man, how many times have I said this? Holy guacamole. What is Kc equal to? In general, it's the concentration of the products divided by the concentration of the reactants. But at what time, specifically at what time are we talking about?
Equilibrium.
Once we've reached equilibrium. We don't care about initial. Initial doesn't matter to us, okay? It can be useful in helping to determine what happens, but we only care about equilibrium concentrations, right? Okay, let's go through an example. Chlorine and carbon monoxide gases are mixed in a 1 liter flask, and the following equilibrium is established. So we've got carbon monoxide and chlorine reacting together to make COCl2. Good, okay, awesome. Initially, 3.4 moles of chlorine was present with 1.75 moles of carbon monoxide. At equilibrium, 0.8 moles of carbon monoxide was found. So our goal is what is the Kc for this reaction? That's what we want to know. Okay. What is Kc? You can only really get Kc from doing your Kc expression. We need the concentration of the products at equilibrium, and we need the concentration of the reactants at equilibrium. Do they give us the concentration of the products and the reactants at equilibrium? No. They kind of give us one. Would you agree?
Yeah.
They kind of give us one equilibrium value. So what I'm going to do, I just want to be very clear about this. Initially, blah, 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 equilibrium, blah, 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 blah. What do you immediately know we have to use? Initially, something equilibrium. We have to use an ice table. We have to use an ice table, okay? So let's do this. 3.4 moles of chlorine. All right, so let's write our reaction above here. Carbon monoxide plus Cl2 gives us CoCl2. Do you remember the first thing that we should do when dealing with an ice table, if we can? Chelsea?
Assume there's 0 products.
Pardon?
Assume there's 0 products.
No, not the first thing that we should do, okay? We'll do that here in a second, maybe, okay? What unit do they give us?
Moles.
They give us moles, but what do we actually want it in?
Moles per liter.
9 times out of 10 we want it in moles per liter, okay? So let's take our 3.4 moles of chlorine and let's divide it by our volume. What's our volume?
1.0.
Oh, all right.
So this is,
Yeah, are we good?
yeah.
All right. So 3.40 moles per liter, because it's that divided by 1. Good, awesome. At chlorine, nope. That's supposed to go under chlorine. That's my bad. 1.75 moles of carbon monoxide, 1.75 moles divided by 1 liter. Good. Now, Chelsea, what are we supposed to do? Does it say anything about our product initially? No. So what can we assume it is? 0. Good. What's the only equilibrium value they give us? Carbon monoxide. 0.80 of carbon monoxide. So let's go through this, and I know that ice tables are a little bit annoying. Is there any column in here that you can complete?
This.
Yeah, that first column you can complete, right? So what's the change? Was it negative or positive?
Negative.
It was negative 1.05? No, 0.95. Negative 0.95. Okay. If this changed by negative 0.95, what should the next substance change by?
0. Negative.
Should it change by the same? Should it increase or decrease? Should it increase or decrease? Should decrease by 0.95, right? Because if we're losing x here, we should lose x here, and we should gain x here. So what's our CoCl2 going to increase by? Is that okay? Are we happy that for every one of these reacts, we're going to increase by this? Like, it's just, if they're all 1s, then all of the changes should be the same. Is that okay? Because our x is just 0.95. Okay, perfect. Well, can you figure out what the chlorine concentration at equilibrium is now?
2.45.
Yeah, should be 2.45, and this should be 0.95. So can we calculate the Kc now? Yes. Once we were able to figure out all of the equilibrium concentrations, we can use this to calculate Kc. Would you agree? Go ahead and do that for me, please. So under A, write the equilibrium law for the reaction. You can go ahead and do that if you want. And then under B, calculate the value of the equilibrium constant. You can go ahead and do that as well. I'm going to be walking around and I'm going to be trying to help people if they need help. Is it? Okay. It's amazing. I'm going to give you another kind of 10 seconds to just finish up your thoughts. So let's take a look. Let's take a look at our ice table. Let's just take a look at our ice table. And I mean, remember we've got kind of reactants on one side and products on the other side. And so what are you thinking? Does there appear to be more reactants or more products? This one's tough. But does there kind of appear to be more reactants or more products? More reactants, right? So what are we assuming the Kc is going to be bigger than 1 or less than 1? Less than 1. And so, okay, let's try that out. What is the concentration of COCl2? It's 0.95. So 0.95 moles per liter. Hey, how come I didn't use times 10 to the negative 3?
Because it's already in moles per liter.
It's already in moles per liter. It's not millimoles per liter anymore, right? We only use that because it was millimoles per liter. Okay, perfect, no problem. So our concentration of carbon monoxide, 0.8 moles per liter. And our concentration of chlorine, 2.45 moles per liter. So when I do this, I don't know, what are you going to get?
0.484.
0.48?
Yeah, 4, yeah.
Is that the appropriate number of significant digits?
No. Yeah, 4.8. Yeah, 4.85. I get.
I don't know. Do you? Let's take a look at our initial information. How many significant digits do we have in our initial information? I had 3, 3, and 2, right? So I mean, this is kind of implying that we should really only have 2 significant digits. Would you agree? Yeah. So this okay. Right. So this is going to be 0.48. And what are the units on my Kc?
There's no unit.
Nothing. No units. We define it not to be units. What? Would we round up? Is that 5? Does that 5 stay as a 5, or did you round the 4 up to a 5? Did
No,
you?
we round the 4 up to the 5.
The next digit was a 4, right?
Yes.
So now you're double rounding, right? Yeah, you only round once. Only round at the very end of your answer and just round the one time. Okay, perfect. So let's go through some equilibrium law problems here. In general, there's a few different types of problems that I could give you. I could give you all equilibrium information, and you could be asked to calculate the Kc. Now that's probably going to be pretty easy. Would you agree? If I gave you all the equilibrium concentrations, and I just asked you to plug it into an equilibrium law expression, could you do that? That probably wouldn't be that bad, right? So here, the reaction for the formation of hydrogen iodide, blah, right? Okay. Calculate the Kc if the equilibrium concentrations are this. Okay, let's go ahead and do that. That should be fairly straightforward. Kc is always what? Products over reactants. So it's our hydrogen iodide squared over our hydrogen times our iodide, or iodine. So if our hydrogen iodide concentration is 0.0250 moles per liter squared divided by 0.00350 moles per liter. Again, this is one of those things where if both of the bottoms are the same, I'm not going to write it twice. I'm just going to write squared because I'm lazy. Is that like 50 or something like that? $51, right? Yeah. 3 digits, so it's going to be 51.0. Good. Okay. At the exact same temperature, what would be the Kc for the decomposition of hydrogen iodide? Now, okay, this is the formation of hydrogen iodide. Would you agree? The way this reaction is written right here, right now, we're taking the elements and combining them to form hydrogen iodide. So we call that a formation reaction. Well, what would be the decomposition of hydrogen iodide? Would it be the exact opposite of this reaction? You're taking hydrogen iodide and you're turning it into hydrogen and iodine. So, okay, well, let's write that. Let's take 2 hydrogen iodides and let's decompose it into hydrogen and iodine. Would you agree these two reactions are the exact opposite of each other?
Yeah.
Yes. We agree on that? Cool. So what should the Kc values be? What should be the Kc expressions be? Sorry. Should the Kc expressions, if the products in one are the reactants in the other, then should the Kc expression not just be the exact opposite? Right? Let's try it out. The Kc for here is going to be H2 gas times I2 gas over Hi squared. Let's work out what that is. Hydrogen gas and iodine gas have the same concentration at equilibrium, 0.00350 moles per liter. And then the two hydrogen iodide is 0.0250 moles per liter squared. Yeah, all we're doing is we're plugging in this information and we're putting it into the problem. Good. 0.0196 or 1.96 times 10 to the negative 2. Okay. That's great. That's fantastic. There's a shortcut to this problem. Whenever I say something, something, something forwards reaction, and then I say, well, what would the Kc be for the exact opposite of this reaction? I don't know if you know what happened to my Kc expression. What happened between here and here? Would you agree these are the reciprocal of each other? And so all you have to do, the Kc of the reverse reaction is equal to 1 over the Kc of the forwards reaction. I would like you to prove to yourself that that's basically the case, okay? Everybody just go 1 divided by 51, and let's see what we get. 1 divided by 51. Would you agree you get on the order of 0.0196? Yes. Okay. So within 3 significant digits, that'll be fine. That's a little trick that can help you out. Just if I ever say something something this reaction and then I totally flip it something that reaction, then that'll be helpful to you. Hopefully that's okay. Again, we're going to be doing some problems here. I just want to see. We got three more problems, and I would like to do them in the next 10 minutes, and then I'm going to give you some practice. Is that okay? Let's kind of rocket through this as much as we can. So, for this question, is this reaction homogeneous or heterogeneous? It's heterogeneous. Ooh, that's interesting. So let's write the Kc expression. Should I include all of the values?
No.
No. What's the only substance I'm not going to include?
The liquid.
Yeah, the one liquid in here, so water. So this is the hydronium concentration times the acetate concentration. And I'm foregoing states of matter because I'm lazy right now. Good. So far, has this been a difficult question? No. Okay. That's a very good sign because this is sincerely half of the battle a lot of the time. At equilibrium, the concentration of acetic acid is 0.1. The hydronium ion concentration is 0.00133. Calculate the Kc. Now, here's the problem. You don't know this yet, okay? But it's trying to imply to you that the hydronium concentration and the acetate concentration are all 0.00133. So calculate the Kc. So go ahead and try and do that for me, please. Just take these values and plug them into there. Yeah. We'll go through that in chapter 16. You don't have to know that right now. I won't ask you to do that. Just double check that you get the same Kc value as I do. 1.77 times 10 to the negative 5. So is this reaction, let's go back to the reaction at the top. Is this particular reaction at 25 degrees Celsius, is this reactants favored or products favored?
This is less than 1. Yeah, yeah.
I don't know, is this number greater than 1 or less than 1?
Less than 1.
It's significantly less than 1. Would you agree? This is way less than 1. This is about 5,000 times less than 1, right? Okay. So are the reactants or products favored? Well, the reactants are favored at equilibrium because this value is less than 1, right? Good. Cool. 2 more questions, then I'm going to let you giddy up on some own stuff. Write a balanced reaction for the formation of ammonia, otherwise known as the Haber process. So if I ever said write a balanced reaction for the formation of ammonia, okay? We're forming ammonia. What 2 things do we need to form ammonia?
Nitrogen and hydrogen.
Nitrogen and hydrogen. So we need N2 and H2 in order to do that. Could you balance this reaction? Is that what you would qualify as easy to do? I'm trying to get you to think about it as much as you can, right? 2 nitrogens, 6 hydrogens, 6 hydrogens should be good to go. So this is the formation of ammonia. Now the Kc for this process is 3.8 times 10 to the 4 at a very specific temperature. At equilibrium, the hydrogen concentration is this and the nitrogen concentration is that. Calculate the equilibrium concentration of N2. Now,
We need ice.
do we need an ice table? Look very closely at the question and ask yourself, do we need an ice table? I don't know if it's yes, I don't know if it's no, but I want you to try and think of it.
We have the Kc.
We have the Kc.
Yeah.
We have 2 of the 3 equilibrium values, right? Concentrations. When would we use an ice table? Under what conditions would we use an ice table?
The initial one. When we found the Kc.
Sorry, Isaac, go ahead.
Don't know the equilibrium constant.
Yeah, when we don't know the equilibrium constant, maybe. Under what, like, what type of a question requires the use, Matt?
When we don't have the equilibrium concentrations.
When we don't have all the equilibrium concentrations, but this one's saying calculate the equilibrium concentration of N2. So it's saying you don't have all the equilibrium concentrations, right? When would you use an ice table?
When we have the initial volume and the equilibrium.
Whenever a question says initially something, and then it says do something with the equilibrium values, right? That's when you use an ice table. Let's read the question. Does it say anything about initially? Does it say at first something was put into a reaction vessel? No, it says the Kc for this process is that at equilibrium. It jumps straight to equilibrium. At equilibrium, this is that, that's that, find that. We don't need an ice table. In fact, if you use an ice table, you're probably going to go down the wrong direction. In general, what is a Kc equal to? What is the Kc for this reaction equal to?
3.8 times 10 to the power of
Yeah, 3.8 times 10 to the 4, but in general, right?
Product of reaction.
Products over reactants. So what's our only product here? Ammonia, right? What are our two reactants? Hydrogen gas and nitrogen gas. N2 gas. That's a terrible square bracket. Holy. Okay, this is one type of question that I could ask you, okay? And a lot of people get really confused. When do I do this? When do I do that? Well, I'm telling you, it doesn't give you anything about initial, but it is asking you about equilibrium, okay? The only two ways you can figure out anything about an equilibrium are using an ice table or using a Kc value. Those are the only two ways you can figure out anything to do with equilibriums. Ice table or a Kc value. So here, do we have the Kc value for this reaction? Yes. Do we have the equilibrium concentration of ammonia? Read the question. Do we? Yes. Do we have the equilibrium concentration of hydrogen?
Yes.
Do we have the equilibrium concentration of nitrogen? No. I'm curious, does anybody know where this is leading? Algebra. All you have, this is a relationship, this is an equation with one unknown variable. This is an equation with one unknown. You can solve an equation with one unknown variable. All you have to do is rearrange this equation so that your unknown is all by itself on the top of a fraction on the other side, that kind of thing.
Yeah.
Yeah, totally should. That's my bad. That's what you get for being a lazy POS. That's okay. Okay, here we go. So how do I get nitrogen all by itself? How are you going to do that?
Both sides by nitrogen, divide both by Kc.
Okay, so what we're going to have to do, we're going to have to take this expression, and because nitrogen is in the bottom of a fraction, that's not good, right? So we're going to have to multiply by the nitrogen concentration. Would you agree it disappears from the entire right side of the equation, right? That, they cancel. But because we did that over there, we got to multiply by nitrogen over here. So now that we've done that, we've multiplied by nitrogen on both sides, basically all we did was moved it from the bottom side of this side to the top side of that side. Now what's the only thing we need to do?
Divide by Kc.
Divide by Kc. So Kc, when we divide by Kc, it shows up down here now. And that's grade 10, maybe grade 9 algebra, right? So if you need help with that, let me know. Oh man, the square brackets are giving me trouble. Okay. So rearranging, hopefully that was okay. This is the ammonia concentration divided by the Kc and the hydrogen concentration. Thank you. So we could plug our information in. What was the initial? I don't want to scroll up. You read for me. What was the initial, what was the equilibrium concentration of ammonia? 3.1
Yeah.
times 10 to the what? 10 to the negative 2 moles per liter. So that's going to be squared. Divided by the Kc, and the Kc is what? 3.8 times 10 to the 4. Holy guacamole. 3.8 times 10 to the 4. And that's also being divided by the hydrogen concentration, which is 3.1 times 10 to the negative 3. But it's being cubed, moles per liter. I need every single person to do this calculation on their calculator. And I need you to prove to me that you know how to use your calculator properly. Man, hopefully I did that right. I got 0.848896. Okay, please let me know if you can't get that on your calculator. Please let me know if you have a difficult time getting it on your calculator, but otherwise, let me know. And then what are we going to round to? So 2 significant digits, so 0.85 moles per liter. Would you agree?
I don't get the numbers.
You didn't get that number?
No.
Okay, so we're going to have to work on a calculator here in a little bit. Last thing. We can do this really quickly. So a variation for solving Kc. Kc expression for the production of ethanol is this. So there's a reaction. Basically, it's this plus this gives you that. Okay, sure. Under certain conditions, the Kc is 310. At equilibrium, in a 5,000 liter tank, contains 940 moles of ethanol, 190 moles of water. Calculate the equilibrium concentration of C2H4. So I'm curious. Let's take a look at this. Do we have the Kc value? Does it give us Kc in the question?
Yes.
Yes, it does. Good. Check. Does it give us the ethanol concentration?
No, but we can get it.
Yeah, no, but we can get it really easily, right? How would you get the ethanol concentration? How could you get the concentration of ethanol in this? Do you know how many moles of ethanol are in here? How many moles of C2H5OH? 940, and it's in a 5,000 liter tank, right? So the concentration of C2H5OH is just 940 moles divided by 5,000 liters. That's us being tricky. That's us being jerks. 940 divided by 5,000. Hopefully you get that. Yep. It gives us 190 moles of water. So the concentration of water, we should do the same thing, right? 190 moles divided by 5,000 liters. So this is the exact same question as what we did before. Just a little tiny variation where they're giving you moles and you have to divide it by liters because these are concentrations. Now let's go back up here. Do you want to use an ice table here?
No.
No, you don't want to use an ice table. We have Kc. Do we have the concentration of ethanol now? Yep.
Yes.
We have the concentration of water now, and we just want the concentration of C2H4. So we could do that. I want, just take a couple minutes and try it out. Try and make sure you get the same number I get. Just try it out and double check that you get the same things as me. I'm going to be handing out a sheet for everybody. You're welcome.
Get the same one. Yeah.
Okay, let me know if you have any questions about this. If you didn't get that, let me know and I can help you work through it. That sheet that I just gave you, it says equilibrium Kc and ice table problems. Sorry, Kc and ice table, that's what it is. Wednesday, if I can spell. That's going to be due Wednesday. You got 2 days to do it. Yep, that thing right there. Chemical equilibrium, Kc and ice tables. So that's going to be due Wednesday. Keep in mind we have a quiz on Wednesday. Now, most of this stuff is the kind of stuff that you could see on the quiz, right? So if you know how to do this really well, then you'll know how to do the stuff on the quiz really well. As soon as you're done this, you can hand it into the bin, and I will take a look at it.